And actually, my stories are going to be kind of obscure. You might not have heard of them in the news at all. Um, but what I wanted to do is actually begin by talking about a story that I actually did for 60 Minutes in Space more than a decade ago. It had to do with galactic habitable zones. And you might have heard about the habitable zone in our solar system, which is basically the orbital space in which it's neither too hot nor too cold for liquid water to exist surfaces of rocky planets. So this is where you expect life to be able to evolve on the surfaces of planets. And the Earth happens to be in the middle of the habitable zone. In our solar system, Mars and Venus are at the outer edges. But astronomers have also been talking about galactic habitable zones. And the way those are defined is that, well, in order to make planets, you need heavy elements, things that are heavier hydrogen and helium, or as what astronomers call metals. And so the astronomical periodic table, because hydrogen and helium make up most of the universe, and everything else heavier than helium is only a few percent, that few percent get lumped into this term metals. So you'll see that a lot in read writings by astronomers. But so metals are important, these heavy elements, because if you're talking about the Earth is mostly made up of stuff that's not hydrogen, and heavy and metals or heavy elements tend to be formed in stars. So you need lots of those to make those heavy elements, but you can't have too many supernova explosions. If you have too many supernova explosions, what happens is you increase the chance that your planet with early life get wiped out by an explosion. So this was talked about in a paper from 2004, and one of their ideas was that if you look at our galaxy, well, our galaxy has more stars in the center than there are in the outer edges, and so if you're near the center of the galaxy, in the inner galaxy, then the greater stellar density means that there's an increased risk that you might get wiped out by a supernova. So the inner galaxy actually is more difficult to have a habitable world, whereas the middle of the galaxy, which is interestingly enough roughly where the sun orbits, is just right. And then in the outer galaxy, you actually run into this opposite problem where because the star formation rate is lower, there are fewer stars, you have fewer metals, and so it might be more difficult to form planets. And so you have a situation, too many supernova in the center, not enough supernova in the outer regions, in the middle, just right. So that's what they call the galactic habitable zone. And now what happens if you think about not just the evolution of the galaxy, but if you include the evolution of the galaxy. So our Milky Way galaxy was formed over the history of the universe via mergers. So this is what we think actually occurred, and we find evidence of this when we go out and look really far and at distant galaxies. So the more distant the galaxy you look at, the further back in time you're seeing an earlier stage of the universe, and by looking really far away, that gives you a sense of what the early stage in the universe that led to our galaxy must have been like. So very distant galaxies were smaller, and they showed more star formation, and they also showed more evidence of merger activity, where galaxies through gravity merged together, and so you had much more chaotic, irregular-looking galaxies. And over time, as you look at galaxies closer and closer to us, they seem to grow larger, and they grow to be the more regular galaxies that we find today. So just by looking at, by observing distant parts of the universe, we get a sense that there's evolution going on, and this evolution involves collisions and mergers. And here is a simulation of that. And so what the simulation does is it follows the universe after the Big Bang, and as the universe is expanding, the gravity is the other dominant force that's pulling matter together. And so what you're seeing is that gas being pulled into the nuclei of galaxies, and then star formation is taking place, and that tends to heat up the gas. A central black hole can form, and when galaxies merge, those black holes can grow, and things can get really complicated. You can actually see a galaxy here starting to merge with that other galaxy and growing in size. And so you're seeing gas falling in to make the galaxy bigger, and then you're also seeing galaxies, and then at some point we're going to see a really big galaxy. And this number here is the billions of years after the Big Bang. And so the present is 13.5 billion years. And so here, again, we're getting two big galaxies merging. And so we can basically, not totally accurately, but we can, through computer simulations like this, get a pretty good sense of how accurate our models are. And so what we do is we try to compare the distribution of galaxies that we see in these computer simulations to the distribution of galaxies that we see at a certain look-back time. But this sort of scenario basically shows how a Milky Way-like galaxy or a region that includes a large spiral galaxy like our Milky Way can form. So pretty cool stuff. And then whenever mergers occur, what happens is a lot of the gas gets jammed up into molecular clouds, and that can actually initiate new waves of star formation. And whenever you have waves of star formation, you'd expect supernova. And you'll see what, this in sort of graphical form in just a second. So what the paper that I'm talking about was just published, but it basically explores how habitable galaxies are by following the evolution of them through merger trees like the examples that I showed in that diagram just a couple slides back. And what they include in their model are supernovae, just like the very first paper I talked about. If you have a supernova going off, a supermassive star, it blows up at the end of its life after a few million years. The end result is either a pulsar or a black hole. But the amount of radiation that you get from a supernova can effectively wipe out life on planetary surfaces if you're too close to that supernova. So supernova can be extremely dangerous. It turns out that there's also another type of supernova called a gamma ray burst that's even more intense. And these are, again, supermassive stars, but instead of blowing up isotropically, meaning they expand, the explosion expands out in a spherical direction, the explosion tends to get beamed, so most of the energy gets sent out in these narrow jets that are along the polar directions of the star. And what happens is, if you are looking at it like us, towards the equator, you're okay, but if you happen to be sitting along the direction of that beam, you're going to get completely blown away, much more intensely than from a normal supernova. So gamma ray bursts are rare, but they can be potentially much, much more destructive, especially if you happen to lay in the path of those beams. And then finally, the third phenomena that the authors looked at were active galactic nuclei. And so it turns out that almost all galaxies that we look at have central massive black holes. So, and those black holes, in our galaxy, we have a central massive black hole about 4 million times the mass of our sun. In other galaxies, they can be 100 million times the mass of our sun. And so we know that black holes have grown over time, at least in the centers of galaxies. And very early on, when matter is fallen into these central black holes, they get jammed up in the accretion disks, and these can get heat up to tens of millions of degrees, and they can also irradiate the stars around them. So these central massive black holes can be very destructive for solar systems, or for at least for life on solar systems. So this is what the contributions are in their model for a generic galaxy. And so what they find is that, so we're looking at look-back time. So the present is up here. So here we are today. And the very beginning to the universe is down here, and this is 12 billion years ago. And what this number is the amount of stellar mass in a galaxy that's irradiated by one of these processes. So very early on, what you find is basically 100% of the stars are irradiated by the active galactic nuclei, by those central black hole engines. And then as you go later and later in time, there's less gas falling in, and so there's less gas to drive the central black hole engines, and so the amount of irradiation falls off from the AGN. And similarly, you might expect lots of supernova early on, but as the star formation rate decreases over the history of the universe, there are less stars being formed, so fewer supernova, and you get fewer irradiation from supernova. Gamma ray bursts, similarly, you get fewer of them, and then when you add all of them together, you get this black curve here. So even today, you might expect for a typical galaxy, 20% of the stellar mass in a galaxy could have experienced one of these extinction type of irradiation events. Now, what they then do is then run one of these merger trees. So what you're seeing is multiple galaxies, and in the end, they come up with about 36, so about 3 dozen galaxies that they end up looking at. And so over time, so again, 12 billion years in the past is here, and then we go further and further into the towards the present. So the present day is up here, and the masses of the galaxy are actually logarithmic. So this is 100,000 solar masses, 1 million, 10 million. That's supposed to be 100 million, 1 billion, 10 billion, and 100 billion solar mass galaxy. So what you see is overall, galaxies will tend to start on the small side, and then they gradually move over to the larger end as they merge and grow from other galaxies and from gas falling in. But most of those mergers happen early on in the universe, and then they kind of stabilize, and so the masses don't change that much. But these colors tell you what fraction of the galaxies are actually safe from irradiation. So the blue color means 100% of the stars are totally safe for life. But this simulation only shows supernova occurring. So very early on, you can see that almost no galaxies have stars that are capable of life. These are all red. But by about 9 billion years, you start seeing lots of blues and greens. But of course, we know this isn't totally accurate because we're only looking at supernova. What if you looked at supernova, gamma ray bursts, and black hole engines? Well, in that case, you really have to get up to about 6 billion years before you start seeing lots of blue. And so lots of cases where most of the galaxy is safe from these irradiation events. But this is still not totally correct, even for the models that they run. And so one other thing that they do is include in the increase in metallicity, meaning the increase in heavy elements that can create planets. So when you do that, it actually makes things a lot worse. So in this case, you can see up here, there's only a handful of galaxies, maybe a third of the galaxies or less, definitely less than half, that are relatively safe for life. But and actually, they even changed the scale. So this blue isn't 100%; it's actually 60%. So what we find is that less than half, probably on the order of 40% of the galaxies, or the mass of the galaxies, are relatively safe. And there are lots of situations where you can have a periodic event. So you can follow a galaxy along, like this one here, where it's red, and then it gets to blue, and then suddenly there's a gamma ray burst or something, and it goes red once again. And so this simulation shows that perhaps these galactic habitable zones might be rarer than we thought. But the authors also note that there's a caveat that there's a lot of things in their simulations that are approximations, and there are definitely improvements that can be made. But this is still a really interesting model to consider when you think about how probable life is, not only in one galaxy, but throughout the universe, and looking at lots of galaxies.